On November 18th, 2026, at exactly 12:16 in the morning Central Standard Time, a spacecraft built with 1970s technology will cross a threshold that no human-made object has ever crossed before. It will reach a distance of 16.1 billion miles from Earth. At that moment, a radio signal traveling at the speed of light, the fastest anything in the universe can travel, will require a full 24 hours just to reach it, and another full 24 hours to come back. A complete 2-day round trip at the speed of light. The machine that will achieve this is Voyager 1. It is 49 years old. Its onboard computers have less combined memory than the cheapest USB drive sold at a gas station today. Its power source, a decaying block of plutonium, is producing less electricity than a single incandescent light bulb. And what it is sending home from the darkness between the stars is data that is forcing scientists to rewrite the textbooks on what interstellar space actually is. To understand why November 18th matters so profoundly, and why the signals Voyager 1 has been returning from beyond our solar system have left researchers genuinely unsettled, you have to start at the beginning. Not the beginning of the Voyager mission, but the beginning of what scientists thought they knew about the space between stars. For most of the 20th century, interstellar space was imagined as essentially nothing. A cold, featureless vacuum stretching between stellar systems. Inert, silent, dead. The distances involved were so vast that the idea of anything interesting happening in that emptiness seemed almost contradictory. Stars were interesting. Planets were interesting. The space between them was filler. Then Voyager 1 arrived there, and the emptiness turned out to be anything but. Voyager 1 launched from Florida's Kennedy Space Center on September 5th, 1977. Jimmy Carter was in the White House. The first personal computers were just beginning to reach consumers. Star Wars had just transformed American cinema 4 months earlier. The mission was designed to take advantage of a rare planetary alignment that would not repeat for another 175 years, a configuration that allowed a single spacecraft to use the gravity of Jupiter and Saturn as slingshots, receiving enormous velocity boost that no rocket engine of that era could have provided on its own. Voyager 1 flew past Jupiter in March 1979 and sent back images that stunned the world. A close-up view of Jupiter's great red spot as a churning, continent-sized storm, the volcanic fury of the moon Io erupting in real time, and a faint ring system around Jupiter that nobody knew existed. It reached Saturn in November 1980 and revealed that Titan, Saturn's largest moon, was wrapped in a thick nitrogen atmosphere denser than Earth's own. Then, the gravity of Saturn flung Voyager 1 upward and outward, away from the plane of the planets, on a trajectory that would carry it out of the solar system entirely. The planetary science mission was over. The interstellar mission had begun, and nobody alive at the time expected it to last this long. For decades, Voyager 1 traveled through the outer heliosphere, the vast region of space where the sun's influence still holds, where solar wind still blows outward, and the sun's magnetic field still shapes the environment. Scientists monitored the changing readings as the spacecraft moved further from home. The solar wind particles became less dense. The energetic particles from outside the solar system, cosmic rays, became more numerous. The spacecraft was approaching the heliopause, the outer boundary of the sun's influence, where the outflowing solar wind meets the incoming interstellar medium and is pushed back. This boundary is not a sharp line. It is more like a shoreline, where the ocean meets the land, and the two environments mix and churn before one gives way to the other. Like and subscribe, because what Voyager 1 found when it crossed that shoreline overturned models that physicists had spent decades building. On August 25th, 2012, after 35 years of continuous flight, the instruments aboard Voyager 1 registered changes that scientists had been watching for and arguing about for years. The density of low-energy particles from the sun dropped sharply and did not recover. The density of high-energy cosmic rays from outside the solar system surged dramatically. The magnetic field shifted in direction and character. Voyager 1 had crossed the heliopause. It had entered interstellar space. It was the first human-made object in history to do so, and the moment it transmitted that data home, a data signal that took 17 hours and 45 minutes to travel from the spacecraft to NASA's receivers, the scientific community understood that the universe had just changed the scale of human reach in a fundamental way. A machine built in the Carter administration had become humanity's first interstellar probe. What Voyager 1 found on the other side of that boundary was not the quiet, featureless void that the pre-mission models had described. The interstellar medium turned out to be alive with activity. The plasma density, the concentration of ionized gas between the stars, was 40 times higher than the density inside the heliosphere. The magnetic field ran in directions that theoretical predictions had not fully anticipated. And most strikingly, the spacecraft began detecting something that had no clear explanation in the existing models. A persistent, continuous signal coming from the surrounding plasma. Not a burst, not an event. A hum. Quiet, narrowband, and unbroken, detectable across years of data. Cornell astronomer Stella Koch. Hawker, who led the analysis of this signal published in Nature Astronomy in 2021, described it as the faint, persistent hum of interstellar gas. Her senior author, James Cordes, described the interstellar medium as being like a quiet or gentle rain, with the hum as the sound of that rain falling continuously around the spacecraft. Like and subscribe, because a machine that was designed to photograph Saturn's rings is now listening to the sound of the space between stars, and that sound is telling us things we did not know. The plasma hum has allowed scientists to measure interstellar electron density with a continuous precision that was not previously possible. Before this discovery, density measurements depended on occasional shocks propagating outward from the sun, which would trigger brief plasma oscillation events that the instrument could detect. These events happened roughly once a year, leaving large gaps in the measurement record. The continuous hum provides a running measurement without waiting for a solar event. As Voyager 1 moves deeper into interstellar space, the hum allows researchers to map the plasma density along the Voyager spacecraft's path in extraordinary detail, revealing turbulent structures, density gradients, and fluctuations that exist in the medium between stellar systems. None of this was anticipated by the models that existed before Voyager 1 entered interstellar space. The magnetic field anomalies have been equally revealing and equally puzzling. In 2020, Voyager 1's magnetometer registered an abrupt and unexplained jump in magnetic field intensity, accompanied simultaneously by a rise in the surrounding plasma density. Previous similar events had been attributed to disturbances caused by powerful surges of plasma from the sun, striking the outer boundary of the heliosphere and sending waves reverberating into interstellar space. Adam Sabo, principal investigator for the magnetometer at NASA's Goddard Space Flight Center, described this mechanism as a piston effect. But the 2020 anomaly did not fade in the pattern that previous disturbances had followed. It persisted, and in 2024, the magnetometer registered a sudden sharp shift in the direction of the ambient magnetic field that does not correspond to any predicted structure in the interstellar medium at Voyager 1's current location and trajectory. Something is out there that the existing models did not predict, and the spacecraft is the only instrument humanity currently has that can measure it from the inside. The rhythmic pulsing detected in 2025 data from the plasma wave subsystem is perhaps the most genuinely puzzling of all the anomalies Voyager 1 has returned. Where the instrument had previously registered a relatively steady hum of interstellar plasma emission, 2025 data showed regular, repeating variations in the signal at consistent intervals. Random noise does not have rhythm. Random noise does not repeat at consistent intervals. The measured pattern was coming from a region of space that every existing model classifies as quiet and structurally unremarkable. Scientists have proposed multiple candidate explanations. Density waves from ancient supernova remnants propagating across enormous distances, interactions with galactic-scale magnetic field structures, plasma bubble boundaries whose positions are not yet fully mapped, and shock structures carried by the interstellar medium from catastrophic events that occurred billions of years ago and light years away. None of these explanations has been confirmed. None has been ruled out. The most straightforward mechanisms remain the scientific default, and researchers are pursuing them carefully. But the signal is real, measured by an instrument operating at the boundary of its power budget, returning data that nobody fully anticipated. Like and subscribe, because the universe has been waiting beyond our solar system with information that our models were not built to handle, and Voyager 1 is the only messenger we have. Against this backdrop of real and accumulating scientific mystery, the instrument shutdowns of 2025 and 2026 carry a weight that goes beyond routine mission management. NASA turned off Voyager 1's cosmic ray subsystem in February 2025. This instrument had been measuring the energy spectrum of cosmic ray particles streaming through interstellar space since 1977, providing data on how these particles are accelerated and how they propagate through the medium between the stars. 47 years of continuous measurement ended by a single command that took 23 hours to reach the spacecraft. In April 2026, the low-energy charged particle experiment was shut down, another instrument that had measured ions, electrons, and cosmic ray particles since launch. Kareem Badaruddin, the Voyager mission manager at JPL, said publicly that the shutdown was the best option available given the power constraints, and that the team did not rule out reactivating the instrument for future measurements if the power situation allowed. The qualifier matters. There's data those instruments could still be gathering in a region of space no other instrument will sample in our lifetimes. The power situation that forced these decisions is simple physics that cannot be argued with. Voyager 1's 3 radioisotope thermoelectric generators, nuclear batteries, that convert heat from decaying plutonium-238 into electricity have been losing power at approximately 4 watts per year since 1977. As of mid-2026, they are producing less than half of their original output. Every watt of remaining electrical budget must be allocated with surgical precision. The fuel lines that control thruster firings for antenna pointing must be kept warm enough not to freeze. The computer systems that manage spacecraft health must be kept running. The deep space network receivers on Earth that capture Voyager's faint signal must be given something to lock onto. These requirements are not optional. If the thruster lines freeze, the spacecraft loses the ability to keep its antenna pointed at Earth, and contact ends permanently. Every instrument that remains powered must earn its place in that constrained budget. What remains operating as Voyager 1 approaches the 1 light day threshold in November 2026 is a stripped down but extraordinarily valuable scientific suite: the magnetometer and the plasma wave subsystem. These are, not coincidentally, the two instruments most directly positioned to continue monitoring the anomalies that have been accumulating in Voyager 1's data. The magnetometer measuring the direction and intensity of the ambient interstellar magnetic field. The plasma wave subsystem listening to the hum, the oscillations, and the rhythmic pulsations in the surrounding plasma. NASA has a plan to extend both instruments' operational lives. The operation, which engineers have informally called the Big Bang, involves a major power reconfiguration aboard both Voyager spacecraft, swapping powered systems for lower power alternatives in a coordinated maneuver designed to free up enough electrical budget to keep the critical science instruments running for additional years. Engineers plan to test the procedure on Voyager 2 first in mid-2026, and if successful, to execute the same reconfiguration on Voyager 1 no earlier than July 2026. A successful Big Bang on Voyager 1 could even allow the low-energy charged particle instrument, shut down in April, to be briefly reactivated. Like and subscribe, because if the Big Bang works, humanity gets more time with the only instrument it has sampling interstellar space in real time, gathering data from anomalies it does not yet understand. The November 18th, 2026 milestone that NASA officially announced on June 17th carries a meaning that is both practically significant and philosophically staggering. At 12:16 in the morning Central Time, Voyager 1 will become the first human-made object to be 1 light day from Earth, which is 16.1 billion miles, or 173.14 astronomical units. From that distance, if engineers transmit a command at midnight on a Monday, they will not receive confirmation that the spacecraft executed the command until the early hours of Wednesday morning. 2 full days at the speed of light. The delay changes the operational character of the mission profoundly. Every decision about instrument management, every command about power allocation, every response to an anomalous reading must be transmitted with the understanding that almost 2 days will pass before the team knows whether the spacecraft received and acted on it. This is not a communications challenge in any earthly sense. This is correspondence across interstellar distances, slow and precise and irreplaceable, with a machine that is running out of time. To put what Voyager 1 has actually achieved into perspective, consider that 1 light day is approximately 5.6 times the distance from Earth to Neptune, the outermost planet. The entire planetary solar system, the realm of all 8 planets, fits inside a sphere that occupies less than a fifth of the distance Voyager has already traveled. And yet, in astronomical terms, the spacecraft has barely moved. 1 light day is approximately 0.0027% of the distance to Proxima Centauri, the nearest star beyond our Sun. To cover that remaining distance at Voyager 1's current speed would take approximately 74,000 years. Voyager 1 is not heading for another star. It is heading into the permanent darkness between stars, a journey without destination, a drift that will last longer than human civilization has existed and longer than any institution on Earth can possibly track. In approximately 300 years, the spacecraft will reach the inner boundary of the Oort cloud, the vast spherical halo of frozen objects that surrounds the Sun at enormous distance. It will take another 30,000 years to pass through the Oort cloud entirely. In 40,000 years, it will pass within 1.7 light years of a faint red dwarf star called Gliese 445, a close approach by cosmic standards, though it will not come anywhere near the star itself. And then it will continue, for millions of years, orbiting the center of the Milky Way, a silent artifact of a civilization that may no longer exist in any recognizable form. The golden record mounted on Voyager 1's frame carries the sounds of Earth, greetings in 55 languages, music from Bach to Chuck Berry to Indian classical raga, the sound of rain and surf, and a mother's first words to a newborn child. It carries images of human anatomy, food, architecture, and mathematical concepts. It carries the coordinates of our Sun relative to 14 pulsars, a kind of cosmic address that Carl Sagan hoped might allow any civilization that found the spacecraft to locate us. The record is made of gold-plated copper and is expected to remain physically intact for at least 1 billion years in the vacuum of interstellar space. Long after Voyager 1's power has failed and its instruments have gone permanently dark, the record will continue traveling, carrying Earth's introduction into the galaxy. A message from a species that built a machine capable of escaping the gravity of its own star. Like and subscribe, because the scale of what that machine represents, what it has already done, and what it is still sending home right now from beyond the edge of our solar system, is one of the most extraordinary stories in the history of human civilization. What Voyager 1 is encountering as it travels deeper into interstellar space is not nothing. The hum is real, the magnetic anomalies are real, the rhythmic pulsations are real, the plasma density structures that no model fully predicted are real. The mission's data is actively reshaping what astrophysicists understand about the medium that fills the space between stars, and it is doing so with instruments that were designed to photograph planetary atmospheres, running on power that was designed to last a decade, guided by computers that have less processing power than a modern refrigerator. Thermostat. None of this was supposed to still be happening. The fact that it is happening, that a machine launched in 1977 is returning genuinely new and genuinely puzzling data from a region of space no instrument has ever directly sampled, is something that the scientists who have spent their careers on this mission describe with a kind of reverence that is rare in the normally careful vocabulary of professional science. On November 18th, 2026, when Voyager 1 crosses one light day from Earth, it will not be announcing the end of its story. It will be marking how far that story has already gone, and signaling that there may still be more to tell before the last instrument falls silent and the signal fades forever into the dark. The scientists who still report to work every day on the Voyager mission are operating in a mode that has no real parallel in any other field of human activity. They are managing a spacecraft whose round-trip communication time is measured in days, whose power budget is so constrained that one additional powered system could threaten the antenna pointing that keeps the mission alive. Every data point that arrives from Voyager 1 R1 is irreplaceable in the most literal sense. No other probe is anywhere near that region. The next mission to reach interstellar space will travel a different path and will not taking along its specific trajectory. The data from this location, gathered by these aging instruments at this specific moment in the spacecraft's descent toward silence, exists nowhere else and will never exist again. That is the weight the Voyager team carries when they decide which instrument to keep and which to shut down permanently. The universe is not finished talking. Voyager 1 is not finished listening, and the window in which that conversation is possible is measured now, not in years, but in the remaining useful life of a magnetometer and a plasma wave antenna powered by a nuclear battery that has been decaying for 49 years in the cold between the stars. Everything that machine still sends home is a gift from the 1970s to the present, and everything it has already sent home has changed the picture of what lies beyond the edge of the solar system in ways that astronomers are still working to fully absorb. Like and subscribe, because the final chapter of the greatest voyage in human history is being written right now, one radio signal at a time, across 16 billion miles of interstellar darkness. When Voyager 1 crosses one light day from Earth, it will have accomplished something that no engineering specification ever demanded of it. It was built to reach Saturn. It was designed with a 12-month mission lifespan for planetary science. The people who built it gave it the best components available at the time. Components never tested for 50 years of operation in interstellar space, never expected to be transmitting when the engineers who built them had long since retired. The fact that it is still operating is not a triumph of planning. It is a triumph of the margin that careful engineers build into hardware when they do not know how long something needs to last. That margin, multiplied across 49 years and 16 billion miles, has produced the most distant human artifact in history. Still alive, still measuring, still sending home data that nobody predicted it would live long enough to collect. Whatever the plasma hum turns out to be, whatever the magnetic anomalies ultimately mean, the machine that found them was supposed to be dead before Ronald Reagan took office. Instead, it is crossing one light day from Earth in November 2026, and the things it is telling us from that distance remain, as yet, unexplained.